All right. Thank you very much, Annalise, and thank you to everyone who's joined us for the latest installment of the Institute for Carbon Removal Law and Policies Explainer Series. The Institute is a think tank based at American University that seeks to look at critical issues, especially in the context of the social sciences and the law associated with the emerging technologies that fall under the broad rubric of carbon dioxide removal. And today's topic is enhanced mineral weathering. And we have a couple of experts that have joined us to discuss this issue. I'll say at the outset that we initially had three speakers, including Dr. Phil Renforth, but he appears to be having some difficulty perhaps accessing the site and may join us later. But as a consequence, what we're going to do is we're going to have Greg Dipple, who is a professor in the Department of Earth, Ocean, and Atmospheric Sciences at the University of British Columbia, do the initial framing of what we're talking about here in lieu of Phil. And then we will move to David Keller, who serves as a scientist at the GEOMAR Helmholtz Centre for Ocean Research in Kiel in the Biogeochemical Modeling Department. And if Phil is able to subsequently join us, we'll have him supplement some of the remarks in terms of the overview of enhanced mineral weathering. And so with that, I'd like to turn it over to Greg for some initial framing, and then David. And then we have carved out substantial amounts of time, as usual, for questions at the end for the members of the audience. So with that, I'll turn it over to Greg.
Great, thank you, and welcome everyone. I'm going to go ahead and walk through some slides that Phil Renforth prepared to frame today's discussion. I'll go through the first few of those, and then if he's able to join us, he'll be able to fill us in on some of the details. So I'm sharing a screenshot right now of a slideshow for slides that Phil put together. We're looking at the enhanced weathering as a way to mitigate climate change, in particular a way to capture and store carbon dioxide. And weathering is normally thought of as a process that happens over long time scales, over geologic time, as mountain belts are worn down, the minerals are specifically in chemical weathering, the minerals are dissolved, and the cations, or the metals that come from those minerals, such as calcium and magnesium, can then absorb CO2 during the chemical reactions of weathering, and that then pulls the CO2 to be present either in an aqueous phase, or subsequently, if that aqueous phase precipitates carbonate minerals, we can put the CO2 into a solid rock form. And this process is very important over long term. So we think of the long-term carbon cycle. This is a very important process. In fact, it's putting carbon where it likes to be, thermodynamically stable, and more than 90% of carbon on Earth is actually present in mineral form, demonstrating the size of the reservoir and the stability of that reservoir. This slide shows two mechanisms we can use to try and do this as a sort of as an industrial process. We can use natural minerals, so we can essentially accelerate chemical weathering by extracting rock and crushing it so that it is highly reactive on short time scales. Another route is to take alkaline industrial wastes, which are produced by a number of industrial streams, including steel production and many other streams that generate large volumes of alkaline wastes. And when these interact with solutions, then they can either could be used to put bicarbonate into the ocean, so storing alkalinity where the carbon is stored as part of the seawater. This helps to mitigate ocean acidification. Alternatively, if those solutions are used to precipitate, to bind the metals with CO2 to make carbonate minerals, then we can store the carbon in a solid, dense form, and that we can think of as happening predominantly, perhaps, in terrestrial environments or on land. The materials that we can use for this, we think often of silicate minerals. So the minerals shown on this slide here include olivine, elastite, chrysotile, which is a form of serpentine, and tobermorite. These are all sources of alkalinity when they're dissolved, and that alkalinity is generated by the dissolution of the magnesium or the calcium from these minerals. They can then be used to form carbonate minerals, magnesium carbonate minerals, or calcium carbonate minerals. Alternatively, the calcium and magnesium in solution would be balanced by CO2 in solution in alkalinity. This slide shows the different rock names and some different minerals, and it shows their calcium and magnesium content as a function of silica content. So this is just meant to illustrate that we focus on these ultra basic minerals such as minerals such as olivine and pyroxenes. These are present in ultra basic or ultramafic rock types, and they have the highest storage capacity, but that many other minerals on Earth also have this capacity as well. So Phil, if he's able to join us, will be able to walk through this slide in more detail. It talks about a number of industrial routes towards generating that alkalinity in terrestrial environments and feeding it to the ocean. And perhaps at this stage, I will hand off to David to let him talk about his work, and then I can come back and talk about terrestrial environments subsequently.
Thank you very much, Greg. David?
Okay, so what I want to talk to you about is Earth system modeling of enhanced weathering. Let's see, can everybody hear me? Yeah, okay. So when I'm talking about Earth system modeling, I'm going to be talking about models that try and simulate the Earth's climate. And these models have different components like an atmosphere, an ocean, the land, and they also simulate biogeochemical processes. I'm thinking of the carbon cycle here, but also other nutrients as well. And they have vegetation on land and processes in the ocean like phytoplankton and food webs there. But the main reason we use them is because they can simulate the Earth's climate. So I would say modeling of enhanced weathering is still in its infancy, but models have been used to assess the concept of enhanced weathering, not really the technology or how you would actually do this in reality, but they've tried to see, just does the concept work if we try and simulate this in an Earth system model. So far, most of the studies have been looking at large or maximum scales of deployment. They basically assume perfect technology exists, and you can just enhance weathering. You can do this by just increasing the alkalinity in the surface ocean. And the studies have asked questions like, would the idea work if we could do it? Can it reduce atmospheric CO2 as a means of climate change mitigation? Does this limit or even reverse climate change? And then what are some of the side effects if you do this? So I think obviously one reason why you'd use Earth system models is because they can simulate the climate, which is something you want to know about, but they can project into the future, which is when enhanced weathering potentially could be done. As part of these simulations, they simulate the carbon cycle, and understanding how the carbon cycle responds to enhanced weathering is the key for determining the efficacy of this method as a climate mitigation measure. And in a minute, I'll have a slide that'll show why it's important to really understand how the carbon cycle responds to enhanced weathering. But before I get to that, another reason why you use these models is because we can simulate some important side effects that may occur if you do this at a large scale. So now I'll show my first slide here. Share the screen. Okay, so now I want to explain why it's really important to understand how the carbon cycle responds when you do something like enhanced weathering. So what I'm showing here is a very simplified representation of the carbon cycle. We have carbon in the atmosphere, CO2. There's carbon pools in the land, the ocean, and in geological storage. That's where the fossil fuels are. Now, normally the land and the atmosphere and the ocean and the atmosphere are exchanging lots of carbon all the time. There's also a flux of carbon from the land to the ocean. On longer time scales, you also have carbon going from the land to geological reservoirs, as well as from the ocean to geological reservoirs. And then on the outside here, when a volcano erupts, that's when you naturally move carbon from the geological reservoir to the atmosphere. This is simplified, but I want you to keep these arrows in mind on the next few slides, because the next slides are only going to show the perturbations of the carbon cycle and how it responds to what we're doing now by burning fossil fuels, as well as what would happen if we tried to do enhanced weathering to mitigate climate change. Let's see. So when we've burned fossil fuels, what we've done is we've moved a lot of carbon from the geological reservoir to the atmosphere. Now, not all of this carbon has stayed in the atmosphere. About half of it, a quarter, has been redistributed naturally to the land. So that's taken up about a quarter of the carbon that we've emitted. And the ocean has also taken up about a quarter of the carbon that's been emitted. So only about half of that stayed in the atmosphere. And that's where, of course, it has a greenhouse gas effect, and we get and it forces the climate, and we get warming. We've also accelerated the flux of carbon from the land to the ocean. So this is what we've currently done, and why we have one of the major reasons why we have climate change. Now, if we want to do something like enhanced weathering as a means of mitigation, I'll show you that in the next slide. And first, I'm going to show the case of ocean alkalization, where you'd increase the alkalinity of the surface ocean by adding some mineral, and then I'll show a slide on terrestrial weathering. So if you're still emitting fossil fuels, say if we started, in the next few years to try and do some ocean alkalization and increase the surface ocean alkalinity to try and get the ocean to chemically take up more carbon. So if you're still emitting CO2 or burning fossil fuels, you're still moving carbon from the geological reservoir to the atmosphere. Then if you get the ocean to start taking up a lot of this carbon, well, this is going to change the gradients and the amount of CO2 in the atmosphere. And what the models have shown is that your natural land carbon sink will weaken in response to this if you have a major drawdown in the ocean. So that the carbon cycle starts to respond. If you do this enough and you get to the point where you're actually no longer emitting fossil fuels, but you're just doing lots of ocean alkalization, so you're moving a lot of carbon from the atmosphere to the ocean as a means of mitigation, then the modeling studies have shown that the land can actually become a source of CO2 to the atmosphere. So what the land has taken up before, now you have to basically, you can think of that as a carbon debt that's some of it's going to go back in the atmosphere, and then the ocean has to take that up again. So this opposes your carbon dioxide removal via ocean alkalization. And understanding this is really important if you want to get at the efficacy of how well this method would work, and also if you want to be able to monitor and do some accounting when you're doing something like ocean alkalization. If you're going to do enhanced weathering on land, it's a little more complicated. So this shows net negative emissions with enhanced terrestrial weathering. So then you're trying to get the land to take up more carbon. Some of this may be mineralized and be returned back to the geological reservoir, but over a long enough amount of time, you actually may have some of this alkalinity will reach the ocean, and then the ocean can also continue to take up carbon. So that's hopefully a simplistic view of how some of these pathways in the carbon cycle will respond to enhanced weathering. And this, of course, is really important for monitoring and counting and measuring the efficacy of any of these methods. Let's see, so now, of course, that's a simplistic view. Let me stop sharing my screen here for a second. So that's a simplistic view of how the carbon cycle would respond. There's other factors too, but what would happen if we actually wanted to do this? So what do the models show if we actually try and add alkalinity to the ocean? And I'll share my screen again. I'm going to show you an example from a study by Gonzalez et al., where they added a massive amount of alkalinity to the ocean. So the first figure here shows the cumulative amount of alkalinity they added starting in about the year 2020. By the year 2100, they had added around 4,000 gigatons of finely ground olivine, or the equivalent if you were going to do lime would be 4.2 teratons of lime. This is a massive amount. To put it in perspective, only about 8 gigatons of coal per year is mined, and about 50 gigatons of sand, gravel, or stone is mined. So adding this amount is kind of unrealistic. It's on a very large industrial scale, but this study is informative because it shows us what the CO2 removal potential of this method is. So what they did is they ran simulations where they had a high CO2 emission scenario, and that's the red line here, showing that by the year 2100, you've emitted a little less than the CO2 reaches a little less than 1,000 ppm. Then they ran a moderate emission scenario where there's not as much CO2 emitted. And what they were trying to do in this study is they were trying to, during the high emission scenario, add enough alkalinity to actually remove enough CO2 so they would be on the track of the more moderate emission scenario. So that's what they did. And when they did this, what they found is that atmospheric CO2 is reduced. So on the left figure showing atmospheric CO2 that shows the run, the red line is the run where it's a high emission scenario without adding alkalinity to the ocean. The green line is the moderate run without adding alkalinity. And what you can't see is on top of that is there's a blue line. And this is the simulation where they ran the high emission scenario, but added that tremendous amount of alkalinity that I showed in the previous slide. You can see that this caused the ocean to take up a lot of carbon. That's in this figure B here. It says ocean carbon uptake. So by increasing the surface alkalinity of the ocean took up a lot of carbon. And what happened is that CO2 was reduced. They were able to basically mimic the pathway of the moderate emission scenario by adding that much alkalinity to the ocean. This also reduced atmospheric surface temperature. That's what's shown in the figure on the top right there, is surface temperature wasn't reduced quite as much as the moderate emission scenario, but they were able to limit warming. Of course, as I said, unrealistic amounts of alkalinity have been added, but this just shows that according to the chemistry and the formulations in these models, if you could do this, it would probably work to remove a lot of CO2 from the atmosphere and limit warming. Let's see. There's been other studies that have looked at things like, rather than adding just a lot everywhere, which is what I showed you in the previous study, is what if you added it regionally or during different seasons? And it looks like there's only a weak dependence on where and when it is added. However, if you add a lot of alkalinity locally, you have large changes in seawater chemistry. There's also some evidence from studies that alkalization is more effective during a low emission scenario. And I mentioned before that studies have also been used to look at side effects. If you added something like olivine, you could end up adding iron and silicate to the ocean, and this would have a fertilizing effect if you did that. So basically, to summarize this, enhanced weathering appears to work in models. You need to account for the carbon cycle response if you want to really get at efficacy. But so far, the deployment scenarios have mostly been idealized or somewhat unrealistic. So far, enhanced weathering has often been simulated in a very simple way. They just increase the surface alkalinity of the ocean. On land, generally, the Earth system models can't fully simulate enhanced weathering. The studies that have been done, they've had to use a series of models where one model passes information to another model that can do more detailed simulations to get some final answers about how it works there. So far, mostly only coarse resolution or system models have been used, and many important processes have not yet been included in models, although it does look like, as I said, as I showed in that study, that in theory, if you could do this, you could remove large amounts of CO2 from the atmosphere, but there's still a lot of more work that we have to do to be able to say, this is a more realistic amount that you could add. These are the side effects, and a sustainable amount of doing this would be something different than what I showed you in that study there. So that's all I have at the moment for that. I think it's probably Greg's turn now, or we're going to take questions now.
So thank you very much for that intervention, David. Phil Renforth has been able to join us now, so I'm going to introduce him and have him do the remainder of his presentation. Phil Renforth is an associate professor in the School of Engineering and Physical Sciences at the Institute of Mechanical, Process, and Energy Engineering at Heriot Watt University in the United Kingdom. And Phil, I'll tell you at the outset that Greg had done an overview utilizing, I believe, your first 4 slides, and it had stopped at the point where you were explaining us the ocean alkalinity process.
Oh, okay. Well, thanks for that, and apologies for being late. I had it in my calendar as an hour later, so maybe it was lost in some sort of time zone black hole there. Thanks for Greg for emailing me with lots of exclamation marks that the webinar was going to start now. So otherwise I might not have turned up at all. And Okay, I can maybe start where Greg left off then. Okay, I think it must have been this slide here. I'll share my screen. Okay, I think I can share that. Okay, and I can see David on the screen, so can you give me a thumbs up that you can see my slides? Great. Okay, so I assume everyone else can as well. In I suppose the previous slides we were talking more generally about the potential of extracting material, extracting rock, and then doing something to it to increase either ocean alkalinity or to produce carbonate minerals. And what the image shows here is sort of very say a high-level cartoon of potential scenarios that might be used to increase ocean alkalinity. And I suppose this isn't exhaustive, but it's supposed to give a sort of rough overview of things that have been proposed. And you'll notice that all of them require the extraction of minerals. So that's what this the far left-hand side of this diagram shows. And then we can use a bunch of different processes to enhance the dissolution of those minerals, to weather the minerals. We can either spread them onto land, which we sometimes refer to as enhanced terrestrial weathering. And through the process of the minerals dissolving in soils, that releases bicarbonate ions into rivers, which are ultimately get transported to the ocean to increase ocean alkalinity. And this is something that happens naturally over long time periods, but it's maybe something that can be sped up by intentionally adding minerals to the land surface. We may also add minerals to the coast, which is sort of in the middle of the diagram, enhanced weathering on the coast. And again, that's something that the potential wave action of the coastal environment and also the high flux of solution through that environment might speed up weathering. We can also maybe do weathering in more confined reactors, and this is something that was initially proposed by Greg Rao. It's the idea of accelerated weathering of limestone. So if we're forming bicarbonate, that opens up the possibility that we can use carbonate minerals as the source feedstock. So if we're forming carbonate minerals, we can obviously not use that as the feedstock because we wouldn't have any effect on climate. But if we're forming bicarbonate, we can actually use faster reacting carbonate minerals. And that could be weathered inside this sort of large weathering reactor on the coastline. And the idea is you would flux seawater through that, releasing slightly harder water, really, alkaline seawater back into the ocean. Or we might create fast reacting minerals in terms of lime production. So taking a mineral, increasing its reactivity. So in this case, it's taking a carbonate mineral and creating lime, and then adding that to the ocean. There's potentially other ways that we can increase reactivity of minerals, like increasing the crushing and grinding, or putting them through some other chemical processes. But the point I like to make with this slide is that if you look at across all of these, we might be thinking that we don't do any of this already, but actually that couldn't be further from the truth. Well, at the moment, natural weathering does something like on the order of a gigaton of CO2 per year. So that's relatively quite small for the problem. And if we need to do several gigatons of CO2 per year, we're going to need to increase natural weathering by quite a lot. But if you look at the supply side of this diagram, well, we already produce extracting rock is the largest thing we do as a species, or one of the largest things we do as a species. It amounts to something like 50 gigatons of rock per year. And there's probably something on the order of a few gigatons worth of waste material that is too small to sell as aggregate. So that material just sits on sites, on quarries, and it's too large. It's too small to sell, but it's probably too large for what we intend to use it for. But that material is potentially available. We add something on the order of hundreds of millions of tons of rock to the land surface every year. Mostly that's calcium carbonate limestone, but some of that is also basalt, so we do add volcanic rocks to the soil, sort of remineralize some agricultural soils. We do something on the order of 4.5 gigatons of cement per year. So it's pretty amazing to think of that we heat up something on the order of around 8 billion tons of raw materials for that process to 1,000 degrees, or even over 1,000 degrees. It's an enormous engineering industry. We add something on the order of 1 billion tons of material to our coastlines every year, mainly as coastal defense. And we also ship and move something on the order of 10 billion tons of material across our oceans. So this is kind of hand-wavy in some ways, but it's making the point that we do things on the gigaton scale already, and we would be manipulating systems marginally to achieve, or notionally marginally to achieve gigatons worth of CO2 drawdown. The only thing within this that we don't do at a particularly large scale is increasing ocean alkalinity, which we do a little bit around the shellfish industry, but not at an enormous scale. Another point I'd just like to make about this space, and maybe David mentioned this already, was that current experimentation around increasing ocean alkalinity is really not there. I mean, we've done a lot of work over the last 20 years on thinking about ocean acidification, but that interrogates a completely different set of parameters. So, on this diagram, which shows alkalinity on the x-axis and PCO2 on the y-axis, experimentation on ocean acidification is really concerned with this space here. Whereas if we were to intentionally increase ocean alkalinity, we'd be looking at maybe modifications in this space. So a lot more work really needs to be done experimentally on what the impacts are of increasing ocean alkalinity on marine ecosystems. And we can't just think about this as reverse ocean acidification. It's completely different in the change in chemistry of the ocean. So I'd just like to finish on maybe outlining a couple of challenges that we have, and there's obviously technical challenges around the engineering. I don't think these are necessarily insurmountable. There's certainly things that keep me interested as an environmental engineer about developing systems and technologies, and certainly something there that needs to be done, but I don't think they're necessarily insurmountable. But I think what sort of motivates us within this space is that some methods do appear capable of delivering atmospheric CO2 drawdown at multi-gigaton scale for under $100 per ton of CO2. Now that is really quite important when you think of other approaches within negative emissions space. Being able to do multi-gigatons of CO2 per year at less than $100 per ton is really quite a motivating factor, I think. But of course, there are important environmental implications that we need to understand about maximizing benefits. So, thinking about these processes as a way of either developing secondary products, which some systems can do. We can potentially use these as a way of ameliorating the effects of ocean acidification. We can also potentially use some minerals as fertilizers on agricultural fields. And there's potential benefits within this space that really need to be explored, as well as the negative consequences, which I think probably are the first things that come to mind when we think about this, about secondary, about metal dissolution, about potential impacts on ocean ecosystems or on terrestrial ecosystems, and around the environmental impact of mining, which isn't actually as simple as you might initially think when not all mining produces the same environmental impact. So it's quite a complex picture. And I suppose, lastly, I'd like to flag up that there are, of course, societal and governance issues around this space. And if it wasn't already mentioned, there was an excellent webinar by the Institute earlier this month, which I think you can get on YouTube, which talks about some of these issues, particularly around the ocean. But of course, there are issues around the sort of terrestrial and national side as well. So yeah, again, apologies for being late. I'm deeply embarrassed by it, but I'm more than happy to answer questions and take questions if any crop up. So thanks a lot.
All right, thank you very much, Phil. And now I'm going to turn it back to you, Greg, for the final intervention.
Great, thank you. So I'll just add a few words about starting to try to do this at industrial scale. I think that David and Phil made some really important points about us needing to understand the full life cycle carbon footprint of activities that we undertake, and need to understand how it's going to impact the carbon cycle more broadly, as well as an understanding of the other environmental impacts. But in that landscape, we also need to start doing things at a large scale. And so I think when we're talking about removing gigatons of CO2 from the atmosphere, we're talking about, as Phil implied or outright said, large-scale industrial processes. So my research group at the University of British Columbia, actually, we work in the terrestrial side of this. Just get my screen sharing going here. We work in the terrestrial side, particularly with the mining industry. So we're looking at working with the mining industry in the short term to help them reduce their carbon emissions. And an added benefit from this is that we can take the learnings from that to get a better understanding of the large-scale footprint of these processes and also their costs with to help determine whether or not this is going to be an appropriate way to mitigate climate change. So the process we're looking at is, we refer to it as carbon mineralization. We're essentially taking carbon dioxide from the air, for example, combining it with these metals such as magnesium and calcium, and precipitating magnesium carbonate minerals in a solid form, and we're doing this in a terrestrial environment. Now, our work with the mining sector, sometimes they have power generation on site. So we actually do some field studies or some field pilots where we're using point sources of CO2, such as from an electricity generation plant, but we also do direct air capture. So this we look at both point sources of CO2 for our purposes in working with the mining sector. So this is stuff I probably don't need to go back to in much detail, but normally we think about the short-term carbon cycle on the left as the one that's relevant to climate change and the timescale of our that we live. But of course, what we're talking about today with enhanced weathering is really we're taking processes that normally operate in the long-term carbon cycle and accelerating them to the point where they can have a significant impact on the time scale of the short-term carbon cycle. That's kind of the way I like to think about it. Okay. Get my slide to change here. So this slide just shows some of the examples from some of the areas that we've worked. So we work we work at operating mines, and we've done this on 3 continents, working with several mining companies. And these mining companies are extracting commodities that are hosted in these ultra-basic rocks. And so a waste stream that comes from these mines is finely ground ultra-basic minerals, which are inherently reactive to the atmosphere. We've done baseline studies, such as at the Mount Keith nickel mine in Western Australia, which is shown in the 2 photos on the left-hand side here. We can see that what was a finely ground sand is actually heavily cemented by minerals. Some of those are carbonate minerals. And in a study that we published a number of years ago now, we demonstrated that that mine, which produces 11 million tons of finely ground ultra-basic minerals per year, is capturing about 40,000 tons of CO2 per year from the atmosphere and putting it into mineral form. And if you look at that on the footprint of the mine tailings pile, that's about 2.5 kilograms of CO2 captured per square meter per year and put into mineral form. Now we can validate that in field pilots by using a number of technologies. The photo on the lower right here actually shows a soil gas flux chamber system that was developed by soil scientists. We use it to actually monitor in real time CO2 drawdown from these finely ground materials where they're in contact with air. And we can actually demonstrate with these devices similar rates of capture on time scales as short as a few minutes. So we see capture rates of about 3 kilograms of CO2 per square meter per year in the field example I'm showing there on the lower right. So we have the capacity to study the weathering that happens over decadal timescales with operating mines, and we can use tools such as these soil gas flux chamber systems that we've borrowed from soil science. We can use them to investigate and to monitor how our interventions might accelerate the rates of carbon capture. The photograph in the upper right is actually a photo of a field pilot that we ran at the Gaucho Quay Diamond Mine. It's a De Beers mine in the Northwest Territories in Canada, where we were mineralizing flue gas. In this instance, this is our largest experiment to date. This was a quarter-ton experiment, 6-meter long pipeline that we packed with tailings, and we were flowing the exhaust or flue gas from a diesel generator directly into these tailings, and we demonstrated that carbon was not only captured from the flue gas, but it was also precipitated in as a solid carbonate mineral. So we're able to test these processes in real time, and we're moving up to larger scales. The largest pilots that are currently in the planning stages will be on the scale of about 100 cubic meters and involve about 150 tons of material. So we're starting to scale up to investigate some of the issues that we see at larger scales. So hopefully my slide will change here. So my apologies. There we go. So the advantage we have in the short term is we can work with industries such as the mining sector to test approaches and to improve our learning. And then what we learn from that hopefully will help us try and determine if this can be done in a way that produces a net climate benefit and can be done cost effectively without other substantial environmental impacts. And if we get to that case, then we're going to want to actually be essentially prospecting for where the most reactive rocks are for this approach. One thing we find is that we can think of these ultra basic rocks as having a certain reactive capacity, but they have different pools of cations within them, and some of those pools react very quickly. And so to do this cost effectively, we want to target portions of these rock bodies that are the most reactive on the shortest timescales. And there are some geophysical properties that we can use that can serve as useful proxies for when these rocks are highly reactive. In particular, the density of the rocks and the magnetic susceptibility tend to scale with the types of mineral reactions that generate high reactivity. And so we have a project in British Columbia where we're using existing geophysical databases from remote sensing together with existing bedrock maps of ultramafic rocks in the province to actually come up with carbon mineralization potential indices for all the major ultramafic rock bodies in the province. And we can then put this into a GIS framework so that it can be looked at in the context of other infrastructure to help identify areas where we might be able to do this at a larger scale in the future. So one of the motivations here is we know that there's enough ultramafic rocks on the surface of the planet to do many thousands of gigatons of CO2 capture, but we want to find the maybe 1 or 2% of them that are the most highly reactive, so we can do this in a cost-effective way, should it prove feasible for mitigating climate change. So with that, I will stop sharing my slides and just sort of leave you with the thought that we can partner with industry to start to test some of these processes. And the advantage we have in the short term is that we can help these industries reduce their carbon footprint and piggyback onto large-scale existing industrial processes to do it cost effectively. And the outcomes of that work will hopefully help us to determine if we can do this at a large scale for a climate benefit in the future. With that, I'll be happy to take questions as well.
Great. Thank you very much for that, Greg. And with that, we'll move to the question phase. And as always the case at this series, we have an abundance of them. And my apologies at the outset for probably not being able to work through all of them with the time that we have left, but I'll try to get as many of them in as I can. The first question is, what is the mechanism for land becoming a source of carbon to the atmosphere when OA is used for negative emissions? I think that was an issue that David had discussed, so maybe he should take it.
Okay, yeah, so this is something that the models have shown occurs if you actually get to a point where you have a prolonged period of negative emissions. So you actually have to get to where you're drawing down atmospheric CO2. And there's a couple of reasons for this. The land, uptake by the land, a lot of this, at least for the vegetation, is controlled by a CO2 fertilization effect. So when CO2 increases, your vegetation starts to take up more. If CO2 starts to be drawn down, you start to lose that enhanced fertilization effect. In addition to this, you have respiration from soils, from sort of the vegetation matter, but also soil carbon can be respired. And sort of the balance of this is what's been shown is that when you actually have sort of negative emissions, the land which naturally, I mean, it's been shown, well, in models, and it's also been measured in present day that we have emitted more CO2, the land has started to take up more CO2. So what we think from the modeling is that it will start to release CO2. Now, I should say that there really hasn't been that much work done into this. Only a few models have looked into this, and some models do not show this response. So it's not an absolute guaranteed thing, but it is that the carbon cycle will try and balance itself and redistribute carbon in response to changes in atmospheric CO2. So hopefully that went a ways toward answering that. I'd also be happy to share a paper that I had in 2018 that goes into detail on these carbon cycle responses and feedbacks.
All right. Thank you very much for that, David. Next question. What are current research and development work focusing on in terms of these technologies, and what is the time scale, do you think, that enhanced weathering could become available on a large scale? That wasn't directed to anyone specifically, so any of you can jump in.
I'll jump in. Greg here. Yeah, so the work that we're doing with the mining sector, that I think that is one of the approaches that might be relatively well positioned to move to large scale relatively quickly. I would say within the next, it was going to be 1 year now with things that are happening globally. Probably within the next couple of years, we will have moved to the scale of pilot demonstrations at the hundreds of tons scale, at which point we expect that the larger upscaling of these processes will be taken over by industry and by the private sector and done at a larger scale. As I mentioned, the abundance of the rocks to do this allow for many, many gigatons. Practically, the amount of mining going on globally that for commodities hosted in ultra basic rocks is probably capable of capturing tens to perhaps 100 million tons of CO2 per year if that approach were just implemented with the existing mines. Phil probably has something to add as well.
Yeah, I think I could probably speak a bit to that. The first thing in terms of potential scale in the future is I think something on the order of tens of gigatons of CO2 per year by later in the century is something that I think is not unreasonable to imagine. Although I don't think it really matters too much actually what happens in that sort of time scale anyway. Beyond a few gigatons worth of CO2 per year. I think it's certainly worth, at least from the perspective at which we're sitting now, to develop these technologies. In terms of TRL, it's not really. I think TRL is particularly that applicable to enhanced weathering or to this space hugely. I mean, TRL is quite useful when you're talking about developing widgets or pieces of technology, but when talking about supply chains around around enhanced weathering, a large part of it, the technology is already commercially operational and has been for hundreds of years. I mean, thousands of years if you're thinking about creating lime. Of course, there are components within that system that are still yet to be developed or we don't do very much of. So like increasing ocean alkalinity or adding rocks, particular silicate rocks to the land surface. We don't do a huge amount of that already, but we do quite a lot already around the supply chain, and large parts of the pieces of that are commercially operational. So I think that's maybe what I would say to TRL and to scale. Yeah, and I think there's certainly things that we can do in terms of experimentation and research to try and connect where we are now to sort of upscaling and demonstration. So I agree completely with what Greg has just said.
Great, thank you very much for that, Phil. Anything to add to that, David? Okay.
Not really.
Okay, great. Well, the next question is for you, David. The question wanted to know how much is added to the oceans in the Gonzalez 2016 study, and what would constitute realistic or unrealistic amounts?
Okay. Well, I think cumulatively it was around, if you were adding olivine and it was finely ground so it would basically dissolve almost instantly, it was around 4,000 gigatons of olivine they added by the year 2100. And if it was lime, they added 4.2 teratons of lime. So it's a tremendous amount. What's realistic is really hard to say. I know the economists tell me that if the demand is there and somebody will pay you to do this, there are plenty of alkaline minerals out there and it could all be added, but I think you're going to find that at some point it's not that easy. It's difficult to really find a market for all this. And I think there may also be sustainability issues in terms of what's realistic. We don't really know how biology in the ocean is impacted if you add a lot of alkalinity. So you could potentially find that if you add too much, you end up killing off ocean life. And I don't think you'd want to be adding alkalinity past a certain point. There's also a question of at what point will these minerals start to precipitate out naturally. That's not in these models, but but studies have shown that if you add too much alkalinity to the ocean, you can get it to naturally precipitate out. So there is probably an upper limit, and that's not in these models. But basically what they did in that study is just a tremendous amount to see, does the chemistry as we think we know it work? And it does appear to, but there are some things that the models are missing, as well as, of course, economic and sustainability issues that would put an upper limit on that. I don't know if Phil or Greg has anything to say about upper limits of what you could potentially add.
I think that modeling study was I think it was driven by if you wanted to go from I think RCP 6 down to RCP 2.6, something like that. It was
8.5 to 4.5.
Yeah, so it was almost saying, well, if you did ocean alkalinity and nothing else, then that was what the effects would be. But I mean, I couldn't imagine a world where you would do only ocean alkalinity and no other climate change mitigation. So in some ways, the maximum scale isn't really that, in that sort of context, isn't really that important. I mean, I think I couldn't imagine, gigatons worth of rock being added to the ocean tomorrow. I think that's in some ways a preposterous proposition. But I think in some ways I think as long as we can say that it can do something on the order of over a gigaton worth of CO2 per year, then it's equivalent to pretty much anything else we can do in terms of either negative emissions or climate change mitigation. So, I think what we need to do is compare it to other things that we are likely needing to do. And when we're talking about that, it's on this sort of gigatons, multiple gigatons of CO2 per year scale. And maybe we should be thinking about that and driving our models rather than driving them with scenarios that are sort of shaped around maximum impact on the Earth system. I don't think that's a particularly useful thing to do.
Great. Thank you very much for that. Anything to add to that, Greg?
Nope.
Okay. We'll move on to, we have a number of questions that can be aggregated under a broad rubric of discussing in a little more detail what the potential adverse impacts of these processes might be in terms of in terms of ocean biology or biogeochemical responses. We've talked a little bit about that, but maybe you could amplify that discussion a bit.
Yeah, I think some of those were directed at me, so I'm happy to sort of speak to those. I think there was one on first of all on life cycle analysis, which I suppose would have to include the impact on the ocean. And I think one thing I would say to that is people are thinking about life cycle analyses. I don't think anyone's done a full life cycle analysis on a whole system where the ocean is involved. I think they might have done it on the more terrestrial side, but the point is it's quite hard to build a life cycle assessment inventory for these when we don't quite know what the impact on things like ocean biology is. So formal life cycle assessments aren't really aren't possible, really, I would say, until we get a handle on what the ecosystem response would be. And as to what that might be, I think there was another question there that sort of asks that. Well, again, I'd sort of emphasize that we haven't really done the experimentation, or some of it is really only starting. We've done a few trials in our lab looking at the response of we're looking at corallina algae as sort of responding to increases in alkalinity. Some people have looked at calcifying microalgae as well, and but I'd say that work is only just starting. In terms of what might be predicted from existing experiments, again, I'd sort of emphasize that most of the work in this space has looked at ocean acidification and not alkalinity, although there are a few data points that we might be able to draw conclusions from. And just maybe to signpost you to a paper that a colleague of mine, Leonard Back, wrote last year, again, sort of more theorizing what the potential impact might be on ocean biology. And it really depends on the mineral you use and the technology that you use have an important impact on what the overall environmental impact might be. So we need to be quite specific to the mineral and to the technology. For instance, if you're using minerals that include that are relatively quite pure in terms of the alkalinity, so it's calcium hydroxide, for instance, that will impact only the alkalinity of the ocean. Whereas if you're adding olivine, for instance, well, you might include other elements like silicon and iron and potentially nickel and chromium. Again, might have different environmental impacts. So it really does depend on what mineral we're using and how we use it.
All right.
Did I miss anything else in terms of the question?
No, I think you encompassed them. Thank you so much. We're going to try to slot one more in before the end. The question is, does terrestrial weathering have positive soil impacts similar to claims about biochar?
Gosh, I think that one might have been for me as well. So again, it's difficult to say without that experimentation, and I'd point you into the direction of work that's been done out of the Heriot Centre for Climate Change Mitigation, which is based out of Sheffield University, but there's a whole range of other universities, and they've got a bunch of field trials in different parts of the world, and I think they're maybe only on the second cropping season. So again, nothing's published from that yet. So we are sort of waiting to hear from those experiments. But what sort of has been theorized is that there are potential benefits in terms of replacement fertilizer, so some basalts, for instance, that you might add agricultural fields have potential fertilizing effects. There is, because of the slight increased pH that the soil has, a lower nitrous oxide emissions, and the potential introduction of silica into the soil. I'm led to believe, although I'm not an expert in this, has potential to increase crop resistance to pests, as well as you potentially replacing material lost from soil erosion. So those are the potential benefits that I've heard around terrestrial enhanced weathering. I might have missed some as well. If you want to know more, there is a paper that came out either last year or the year before from David Beeling's group, and I think it was Nature Plants. So I recommend you search for that.
Okay. Thank you very much for that. And that will have to be the last question as we've drawn to the end of the hour. I'd like to, at the outset, thank our speakers, Phil Renforth, David Keller, and Greg Dipple for their comments and answers to the questions. And I'd also like to thank those that have joined us to listen and to ask those questions. This series will continue, I believe. Next, we move on to direct air capture, and I believe after that, discussions of the question of potential moral hazard or mitigation deterrence associated with deployment of some of these technologies that we discuss. And I hope that many of you can join us in the future. Be safe, everyone, until we meet again. Thank you, everyone.